Thank you. So my abstract has been on the board for a while, so hopefully you looked at it. The short version is I'm going to talk about knot invariants coming from perturbed Gaussian integration, zero-dimensional QFT, so finite dimensional perturbed Gaussian integrals. There is a short question and answer session which basically says, are they good for anything? And the answer is yes. Okay? Now, everything is joint work with Roland van der Veen, and there is a URL omega epsilon beta over there, and there are various links to it throughout the talk. You're welcome to check it. You're also welcome to use the QR code. The talk follows a handout, and I hope you all have a copy, though it seems that several people went up to the second floor without getting one. There are more at the hands of Matthias over there and also here. And when I was preparing the handout, I thought, oh, wait, this conference is at least partially in honor of Stavros's birthday, so there should be a happy birthday Stavros banner at the top right of the handout. And I thought, hey, wait, maybe I'll experiment and try and ask ChatGPT to make it. But first I had to know if ChatGPT knows anything about Stavros. So I asked ChatGPT, who is Stavros Garofalidis? And it turns out that ChatGPT knows quite a lot. So here's a picture over here. And Stavros Garofalidis is a Greek-American blah, blah, blah at Shenzhen, and he's also related to the Max Planck Institute of Mathematics at Bonn. That's a nice summary. Academic background and career, again, it's all right. Georgia Tech, Greece, Chicago, impressive. And research interests, impressive list of research interests, we all know it. Selected publications, again, an impressive list of publications. I want to highlight on the Melvin-Morton-Rosansky conjecture because it's joined with me, but it's also the basis in some sense of the talk I'm going to give today. Awards and honors, lots of awards, lots of honors, personal interests. Well, ChatGPT even knows about his interest in beekeeping. So it really knows everything. So I said, make a banner for his birthday. And here's what I got. That leaves something to be desired. So I decided, let me ask ChatGPT to try to improve it. So first of all, can you make the banner related to his professional interests? And that's certainly a slightly better one, you know. This does look like mathematics in the background. But it's still Garofalidis with two Fs. So, but Garofalidis is with one F, not with two. And I have no idea what went on in ChatGPT's brain when I asked this question. I really have no idea. But it came out with this answer. Beats me. But at least the math became a bit more relevant. So I said, Stavros, please, no draw. And here's what ChatGPT gave. And it's getting there. It's actually getting there, except for the picture. So can you replace the portrait there with a portrait of Stavros Garofalidis? ChatGPT says, yes, I can do that. Please upload the photo. I said, but you already have a portrait of Garofalidis because I sent it, because you showed it before. But apparently they cannot use specific images because, I don't know, copyright issues, some issues, whatever. So they made me upload, it made me upload a picture. I uploaded this one and got that, and now that is acceptable. Here is Stavros Garofalidis, correctly spelled, the right picture, formulas that are vaguely relevant, pictures of knots. So it's at the top of the handout. Happy birthday, dear Stavros. Okay. You know, I now have my own acknowledgement, and I have to mention mentioned prior art. What I'm talking about is not in air. It follows work of several other people. In particular, that same paper that I mentioned before, which in some sense started this. And let's start. Maybe, but though I'll still start with the dreams. The dreams are usually at the end of the talk and therefore hardly noticed. But let me tell you what my dream is, and then the talk will somewhat justify. So the dream is that given a knot K with a ciphered surface sigma, here is an example. I found it on the street in Mexico City. So here is a ciphered surface of the boundary of this. So it's a surface. It's embedded in R3. It's orientable. Its boundary is a knot, and in fact, it's a ciphered surface of the trefoil knot. And the dream says is that there is a Lagrangian, basically just a function which looks like a Gaussian plus a perturbation, L sigma, defined on 6 copies, so the direct sum of 6 copies of H1 of the first homology of the surface with coefficients in the reals and with values in the reals, and whose coefficients are low-degree finite type invariants. So for example, the quadratic part of the Lagrangian should somehow be related to the linking form of the ciphered surface. So if you have a ciphered surface and you have 2 homology classes on it, so here is their picture, then their union forms a embedded graph because they intersect. And then you can look at finite type invariants of that embedded graph. For example, the linking number of the 2 components when you split them apart a little bit. And that's a quadratic form on H1, and that would be the quadratic part of that Lagrangian. And then the hope is anyway that the perturbed Gaussian integrals, that the formal Gaussian integral of the exponential of that Lagrangian, call it Z, and this will be explained in a few moments, will be not invariant. Furthermore, as I will show you, it's a very, very strong and very nicely behaved not invariance. And we dream that the formulas are simple and natural and that they have a universal generalization. So there are many we expect many generalizations, and the dream is that there is some universal way to get them. If this doesn't make sense yet, that's fine. This is my dream, okay? It's only a dream. That would be sweet, and even sweeter is the following. So you see, special classes of knots, for example, ribbon knots, have special classes of ciphered surfaces. If you have a ribbon knot, then it has a cipher. So here is a ribbon knot. It's a knot in red, which bounds a disk that is allowed to have self-intersection, but only self-intersection of one particular type, the type shown here. And if you have a ribbon knot, then it turns out that it has a ciphered surface, so you can remove each of these singularities by replacing this with that. And then it has a ciphered surface that has, generally the homology will be 2G dimensional. It will have G classes of homology classes that are represented by the unlink. So all the formulas that will appear here should be much simpler, and therefore you should be able to say something about ribbon knots. The easiest example of this is the Alexander polynomial. For exactly that reason, you can show that the Alexander polynomial of a ribbon knot always satisfies the so-called Fox-Miller condition, whatever that is. And the hope is to do better than that. Anyway, that was all dreams, and let's start with an example. So the example is in some sense related to the Lie algebra SL2, though we are not going to see it. And so let me start describing it. So let T be an indeterminate. let epsilon be a formal parameter whose square is equal to 0. Later I will make the cube equal to 0 and the fourth power equal to 0. For now, the square is equal to 0. And start from a knot. Draw the knot as a long knot, so kind of cut it open and draw it in such a way that at the bottom it's pointing up, at the top it's pointing up, and at each of the crossings the two strands are pointing up. So, you know, the two strands at each crossing must be pointing up. And of course you can arrange it, because if they're not pointing up, you just turn them around. Okay? Now, once you do that, you can label the edges 1, 2, 3, 4, and then each edge has begins starting up and begins pointing up and ends pointing up. So it has an overall rotation number, right? If an edge begins pointing up and ends pointing up, the tangent makes an integer number of rotations. So mark this rotation number as well. In fact, it's 0 here, 0 here, 0 here, and -1 for edge number 4. So the only rotation number that I've indicated is lowercase 5,4, is 5,4, which is -1. All the other rotation numbers are 0. And let me say that if an edge has a rotation number, I cut it artificially one more time just before the next crossing. So here is edge number 5, 6, 7, and 8. Given a knot presented in this way, let me tell you how to write a formal Gaussian integral. Even the word formal Gaussian integral will be explained in a moment. Formal perturbed Gaussian integral. So first of all, it's an integral over r to the 14, 14 being 1 through 7, you ignore the last edge, times 2. And the variables will be called pi and xi. So you have p1 to p7 and xi, x1 up to x7. And the measure on the real numbers is just for normalization. It's not quite the standard Lebesgue measure. It's 2 pi to the -1/2 times the standard Lebesgue measure. And then the integrand will be a product of 4 terms, red, green, blue, and purple, where the red term comes from the first crossing, the green term comes from the second, the blue from the third, and the purple comes from the rotation number. Each of these terms is essentially an exponential of a Lagrangian. So it's a product of exponentials, so it's really an exponential of the sum. So it's really the integral of the exponential of sum of terms, each one having to do with an individual feature of the knot. And here are the formulas. So if you're looking at a crossing between strands I and j, so my convention is that a crossing is labeled by the incoming upper strand and the incoming lower strand. This one is called I, this one is called j. So this one is a crossing between 1 and 5. Likewise, this one is a crossing between 6 and 2, and so on. And then each crossing also has a sign S. In this example, all the crossings are positive, so S is always +1. And then the Lagrangian the local Lagrangian corresponding to a crossing is xi times pi plus 1 minus pi plus xj times pj plus 1 minus pj plus some other mess plus epsilon times the sign times some further mess. I have nothing good to say about this mess, except that it works. You don't have to memorize it because it's on your handout. Likewise, there is a Lagrangian corresponding to having a rotation -1 on edge 4. So having rotation phi on edge I adds the following contribution to the Lagrangian. Again, you don't have to memorize it. That's not the point. I don't remember it, not remotely. Okay? So therefore, Z is the integral of e to the Lagrangian of the trefoil, dp1 to p7, dx1 to dx7, where the Lagrangian of the trefoil is the sum of all of the terms written before, so a red term for the red crossing, a green term for the green crossing, and so on. And then you can compute this integral. I will show you how in a few minutes. And the result is the Alexander polynomial times to the power -1 times the exponential of epsilon times 1 over the Lagrangian polynomial squared times something else which is actually new. Okay? And in general, the result will be delta -1 times the exponential of epsilon times something divided by delta squared, where delta is the Alexander polynomial, times the something new, let us call it rho 1, rho after Rosansky and Overbay, who wrote about it before, and that's all. Now, this is, you can do it for any knot, and you get a rho 1 for any knot, and you know what? Maybe I'll skip explaining the terms of the Lagrangian and just tell you the next theorem. So the theorem is that, well, this rho 1 or this Z is a knot invariant. Namely, it is invariant under the Reidemeister moves, except I have to modify the Reidemeister moves a little bit because I also care about rotation numbers. So for example, there are two versions of Reidemeister 2, and in fact this is slightly wrong because there is actually a third version of Reidemeister 2. Doesn't matter. There's a little bit more moves to check because I also care about rotation numbers. And then there is also the swirl move that says that if you have a crossing and you swirl around it, you add rotations all around it, nothing changes. What's the proof? So the proof is essentially to use Fubini. You need to show that the invariant of the left-hand side of a Reidemeister 3 is equal to the invariant of the right-hand side. You integrate over all the variables that appear within the picture of the move, and namely you decompose the integration. Instead of writing the overall integral as one big integral, you use Fubini and you first integrate over the variables that appear on the left-hand side and the variables that appear on the right-hand side. If those integrals are equal, then whatever you're going to integrate later is not going to change that. So basically that's the proof. Yes?
But for Reidemeister 1 and 2, this is like there is more terms on the right-hand side than on the left-hand side.
Yes, so here you integrate over 0 variables, here you integrate over whatever it is, 4 variables, and the integral over 4 variables is going to give the same answer as not integrating anything. Okay? But now I have to explain what do I mean by integration and how do you integrate. Okay? Easy said, integrate, but you know, it's not so easy. So the goal for this little subsection is to understand how to integrate over Rn, so this is zero-dimensional quantum field theory, the exponential dx x rounds over Rn, the exponential of a quadratic form, so -1/2 aij xi xj, summation understood, plus a term, a perturbation term that should in some sense be smaller. So for example, it could be preceded by epsilon, where epsilon squared is set to 0, or epsilon to the 5 is equal to 0, okay? So how do you integrate this? And the answer is physicists know how to do it. Mathematicians, fewer mathematicians know how to do it. But it's something that everybody should do it. And let me tell you how to do it, though my way of doing it is slightly different than the usual way. Okay? So what I do is I define calligraphic z lambda of x. So I slightly massage this by dividing the quadratic form by lambda, integrating over, changing the variable to y, but within the perturbation, I write v of x plus 1. And then my goal is to find z lambda of x, and if I restrict my attention to z1 of x is equal to 0, if I set x equal to 0, then x disappears, and this is the integral dy of the same thing as is written here with dx. So really my goal is just to compute z1 of 0, okay? In the limit, so if lambda is set to 0, or rather in the limit as lambda goes to 0, you have exponential of negative of a quadratic form, and you know that goes to a bump function, which converges to a delta function. So z0 of x can be computed, and it simply, well, it comes out the determinant of the quadratic form times the exponential of v of x. And then with gij, the inverse matrix of aij, it turns out that you can write a differential equation for z lambda of x, and it's roughly a Hit equation. I'm going to spare you the derivation. It's here on the handout. You differentiate under the integral, you integrate under the differential. I don't know, you do the usual tricks. And at the end, you find that the derivative with respect to lambda of z lambda is kind of a Laplacian operator applied to z lambda of x. But that's a linear ODE. And the solution of a linear ODE is, okay, this is written here. And the solution of a linear ODE is that z lambda of x is equal to the initial condition to which you apply the exponential of the Laplacian, to which you apply the exponential of the operator. Okay? And this, in fact, is the birth of Feynman diagrams. So I'm not going to show it because it's a little bit irrelevant, but if you if you think of the exponential as a sum of vertices, then this is a sum of ways of contracting these vertices using the inverse of the quadratic form, and that ends up being so-called Feynman diagrams. Anyway, so again, I'm not expecting you to understand the details. That's not the point, okay? The point is to get the picture. So in order to integrate, to do a Gaussian integral, I compute something more general, z lambda of x, and I substitute lambda is 1 and x is 0, and z lambda of x is some differential operator applied to some function, okay? And then, so the problem of integration gets reduced to the problem of differentiation, which in principle is easier. Except it's not really what I want, because you see, I want to apply Fubini. I want to integrate time after time. I want to integrate with respect to the first variable and then with respect to the second. So I want the answer for integration to be written in the same language as the input. The input was an exponential, was an exponentiated thing. So I want the answer not to be written straight, I want to write it as the exponential of something. In other words, I want the wrong way. In other words, I want to compute the logarithm of the answer. So I let z sub lambda, not calligraphic z, just z sub lambda, be the logarithm of calligraphic z sub lambda. And then, again, you play game with differential equations. If you have a differential equation for calligraphic z sub lambda, you substitute this thing into it, and you get a differential equation for z, lowercase z sub lambda. And again, it's a differential equation. Now it's nonlinear. And the equation is that the derivative with respect to lambda of z sub lambda is equal to a sum of gij. Gij is the inverse of the quadratic form times second derivatives of z lambda plus a term that has, this is the nonlinear terms, dxi of z lambda times dxj of z lambda. And I'll short this for a functional f applied to z lambda. So in short, the differential equation is d lambda of z is equal to f of z. Okay? Where f is some complicated differential equation, differential operator, nonlinear. I like to call this differential equation the synthesis equation because if you look at it very carefully, you can explain it, you can understand the terms in it, and you can see how it synthesizes connected Feynman diagrams. But that will take me too far aside to explain, so I will not explain it. But it's a lovely story. Anyway, so how do you, next come, how do you solve an ODE? But you know, we all taught it when we taught ODEs, and you use Picard iteration. So if you want to solve the differential equation, d lambda of f lambda is equal to functional f applied to f lambda with a given initial condition, then you iterate f goes to f0 plus the integral of the functional applied to f lambda, and you seek a fixed point. That's Picard iterations. That's how you solve differential equations. That's how you solve it in first year, second year calculus. Okay? And in our cases, the solution is always reached after finitely many iterations. So there is no limiting process here. Okay? You just do finitely many iterations until the solution stops changing, and then until the candidate solution stops changing, and then you got your solution of the differential equation, which means the value of the integral. And then definition, an integral with a g in it is the result of this process, ignoring convergence. So I just define the integral of the exponential of a perturbed quadratic to be the result of this process, and I really don't care about convergence. Okay, all the story about Lebesgue integration was only to motivate me. I really don't care about it. Anyway, you know, I kind of believe in implementation. I never do mathematics unless not never, but I hardly ever do mathematics unless I can write the code that shows that it works. Otherwise, I never believe myself. So here is an implementation. Well, I first load some libraries that have nothing to do with the content of today's talk. Then I define how I want to, the canonical form of an expression, how I want to display my expressions. And then then come the core. And the core is in yellow. And then there are hacks in very, very light pink in the background. So here is the core. Well, first of all, I define blackboard e to mean the exponential. So e to the a times e to the b gets simplified to e to the a plus b. That's how exponentials behave. Then I defined that the integral of e to a Lagrangian, d, a list of variables, v's stands for variables, is a module in which, first of all, I make a table of the second derivatives of the Lagrangian. That's the quadratic form. Then if the quadratic form has determinant 0, then I cannot invert it, and the whole process from before doesn't make sense. So then you return the degenerate quadratic form in red and stop the computation. Otherwise, you invert the quadratic form, and then you find the fixed point of this iterative solution. So you define dz to be a table of the first derivatives of z, ddz to be a table of the first derivatives of the first derivatives, so it's a table of second derivatives, and then you write basically the formula that I wrote before, and you look for a fixed point, and at the end you substitute lambda to 1 and all the variables to 0, because that's what you're supposed to do at the end, according to my scheme. And so this is a messy program. Oh, and it has some hacks in the background. So for example, I sometimes project using a projection that I call $pi, and pi starts as the identity projection, so it doesn't do anything, but later it will be, I will call it the wisdom projection. Like sometimes I know that the integral is equal of something is going to be 0, and then I project it out to save time and make convergence more reasonable, faster, okay? But so basically this is the program. Let's check if it works. So first of all, let's do Gaussian integration. Sorry, just standard Gaussian integral. So let's compute the integral of e to the minus mu x squared. Oh, sorry, it's not even Gaussian integral. It's the Fourier transform of a Gaussian times plus e plus I psi x relative to the variable x. And as we know, the integral, the Fourier transform of a Gaussian is the Gaussian with the inverted quadratic, and that's exactly what you get here. You get e to the xi squared divided by mu. Then let's make it a bit more challenging. So let's make it a shifted Gaussian, compute the Fourier transform of a shifted Gaussian. So it's the integral of the exponential of minus mu times x minus a squared, this is the shift a, plus I psi x, this is the Fourier transform bit, and the result, which I will call f Fourier of g, of Gaussian, is this ugly formula. And just for fun, now let's integrate, let's do the inverse Fourier transform. So let's integrate Fourier transform of g times the exponential of minus I psi x, and the result is exactly what we started from. This is essentially the proof of the Fourier inversion formula. I mean, if it works for Gaussian, for shifted Gaussian, every other function in the world is a linear combination of shifted Gaussians, so it works for all functions in the world. Okay? Roughly speaking. Let's do some more. So now let the Lagrangian, the thing we integrate, the quadratic form that we integrate, be a general quadratic form. And let's compute its integral, of dimension 2 with matrix A, B, B, C. And let's compute its integral relative to x1 and x2, and this is the ugly result that you get. On the other hand, let's compute, first of all, let's set z1 to be the integral of the same thing, dx1, and let's check if z12 is equal to the integral of z1 with respect to x2. Essentially, I'm checking Fubini's theorem. And the computer runs the result, runs the computation, and outputs true. So we've checked Fubini, and I have no idea why Fubini looks so miserable in the picture. He should be happy. Okay? Anyway, one last example just to check that the program is sound. So now my wisdom projection is that if I see a power of epsilon greater than 13, so I add O of epsilon to the 13, so if I see a power of epsilon greater than 12, I drop everything. So this is a computation only up to epsilon to the power 12. And then I compute the integral of the exponential of minus phi squared plus epsilon phi cubed d phi. Physicists would recognize it as phi cubed theory. And I hit enter, the computer outputs that this is the answer. I don't know how to test it. So I enter the denominators, 5, 5, 1, 1, 0, 5, 5, no, sorry, that's the numerator, into Google, web search, and the web search sends me to the online encyclopedia of integer sequences, and the online encyclopedia of integer sequences tell me that the numerators of mass formula for connected vacuum graphs on 2n nodes for phi cubed field theory is 155, 1105, 565, exactly my series, so we're on track. Okay? And now let's finally compute the trefoil. So the features of the trefoil are that the number of variables, the number of pairs of variables is 7. The features are a rotation number, a crossing, and a crossing. And then the Lagrangian of a crossing is, this is the formula from a few pages ago. The Lagrangian of a rotation number is, this is again the formula for a few pages ago. The variables is a table of pi's and xi's. And then I ask the computer, what are the variables for the trefoil and what is the Lagrangian for the trefoil? And I get this answer. And this was again displayed a few pages ago. Except now this is with a higher authority. It's with a stamp of approval by the computer. Okay?
So, Dror,
yeah.
Where did you tell him that I plus, what is I plus 1 and j plus 1?
Sorry?
I mean, at a crossing you would have 4 indices.
Yeah.
And so I was guessing that for the I plus 1, I mean, 1, if the numbers are 1, 2, 5, 6, then, 1 plus 1 would actually be 5. No, like
no. Why? No, the crossings are so
does the crossing really have only 2 indices and not 4?
Because the indexing is by consecutive integers. So the first step was to label the edges of the knot 1, 2, 3, 4, 5. So if the incoming the incoming over strand is indexed I, the outgoing over strand will be indexed I plus 1. And if the incoming under strand is indexed J, the outgoing one will be indexed J plus 1. So there are 4 indices around the crossing, but if I know I and J, I also know I plus 1 and J plus 1. I know the other 2.
But because I saw a P1 minus P5.
P1 minus P5 comes from Pi minus Pj. Okay?
Okay, thank you.
Okay. Anyway, so now I ask the computer to integrate, but again I set epsilon squared to be 0. And this is the answer that I get, and this is the answer that I advertised before. And it's kind of a lousy way to compute row 1, but there is a faster program and more stories at this reference, which I will not show. But let me just tell you, I mean, all of this wasn't an idle exercise. So the pair, delta and row 1, it makes sense to think of them as a pair because in order to compute row 1, you have to compute delta anyway. So the pair delta and row 1 attains 270,000 distinct values on the 313,000 prime knot with up to 15 crossing, and this is a deficit of 43,000. So it misses 43,000 things in some sense. On the other hand, on compare it with the pair Humphrey polynomial and Chovanov homology, both of those are exponential time to compute, or at least non-polynomial time, and they attain only 243,000 values on the same dot, not a deficit of 70,000. In a moment, I will tell you about an even better pair, delta and theta, and that one has a deficit of 6,700, which is really about 10 times better than Humphrey and Chovanov taken together. Yet better than Humphrey and Chovanov, delta in rho 1 and rho 2 and theta can be computed in polynomial time and even for very, very large knot, and I'll show examples in a few minutes. So in some sense, these invariants are possibly the best we have. Hate me, hate the formulas, I don't care. This is the best we have. Okay? Yes?
How are these distinguished in the total set that you're considering? What invariants do they use to distinguish these knots?
Sorry, what do you...
you have,
So there are actually complete invariants, if you really want, coming from hyperbolic geometry, but they're much harder to compute. Yes?
I think these don't distinguish mutation.
Rho 1 doesn't, theta does. I'll show you in a minute. Okay? I think I want to skip the slide that says that this is actually a polynomial time computation. But basically the point is that you have to invert this quadratic form. That is a matrix inversion. That is insanely complicated for humans, but computers actually can do it rather quickly, in fact, in polynomial time. And after that, you have to sum over Feynman diagrams, but the Feynman diagrams end up being like if seeing that epsilon squared is equal to 0, you only get a sum of contribution, one from each crossing. So you get a sum of terms, each one having to do just a single summation over the knot. For theta, it will become a double summation. But it's still just a summation over the knot, which is linear time. And the double summation, well, it's quadratic time. So basically, these are, for a human, this is god-awful, but for a computer, it's not so hard. Okay? Anyway, let me show you, just to convince, a proof of invariance under Reidemeister 3. So here is the left-hand side. And the edges are called I, J, and K, and then the next edge along this I strand is I plus 1, and the next one after is I plus 2, and likewise J, J plus, and then J plus plus, and likewise for K. On the right-hand side, there is a similar labeling. And let's try to, so you see, the variables I plus, J plus, and K plus, so the xi plus and pi plus, and xj plus and pj plus, so the variables corresponding to the middle variables, corresponding to the single plus thing, are never going to occur elsewhere in the Lagrangian. So I can just integrate them right away. So I can write the Lagrangian of the left-hand side. So a positive crossing between strand I and J, a positive crossing between strand I plus 1 and K, that's the second crossing, and so on. And I can integrate it with respect to the middle variables. Likewise, I can write the Lagrangian of the right-hand side and integrate it with respect to the middle variables, and ask the computer if the left-hand side is equal to the right-hand side. If they are equal, we've proven invariance under Reidemeister 3. Under Reidemeister 3. Unfortunately, the computer thinks that they're not equal. Bad news. Let's make a second attempt. Now you have to look a little bit more carefully at the Lagrangian. And if you look a little bit more carefully at the Lagrangian, you realize that the xi variables, so the bottom variables, but only the x bottom variables, are also not going to appear anywhere else. So I can integrate them out also. Basically, you look at the Lagrangian and you see that it never has xi plus 1 and xj plus 1 in it. So therefore, this I and this j is never going to be the I plus 1 of some other crossing. So, is going to be the I plus 1 of the other crossing, but that's not going to contribute to the Lagrangian. So I can integrate the xi, xj, xk variables also. So my second attempt will be to, write exactly the same Lagrangian, and integrate it with respect to the middle variables, but also with respect to the bottom x variables. And I do it, and I ask, is the left-hand side equals to the right-hand side? And the answer is true. So I go home happily, and then I check my notes, and I find I print the left-hand side, and the two sides were equal because both were illegal integrals. Both had the degenerate quadratic form. So that's a bad proof. So now I need to do something cleverer. So I end up needing to do something cleverer. So I need to know that exactly this integral, these two integrals are equal, except my program doesn't know, my Gaussian integration doesn't know how to compute them. So I need to show that these two things are equal for every value of pi, pj, and pk. Because pi and pj and pk are not yet set. They might be coming, their value might be disturbed by other crossings. So I need to know that this is true for every value of pi, pj, and pk. So what I do is I compute the Fourier transform with respect to pi, pj, and pk. So I take the same Lagrangian and I add to it I times pi I, pi, pi j, pj, and pi k, pk. That's the Fourier transform. And now I integrate also with respect to the p's. And now the integral is more balanced because I have an integral of both the bottom p and the bottom x variable and also all the middle variables. And that turns out to be a good, a computable Gaussian integral. I compute, ask if the left-hand side is equal to the right-hand side. The answer is true. And now, just to be safe, I print the left-hand side. It's a big mess. So it was an equality of non-trivial things, not of error messages. And that actually is a valid proof of Reidemeister 3. Likewise, all other Reidemeister moves are proven in a similar way, and if you really want, you can check it on this URL. I have to say that, you must be asking yourself, where is this coming from? I'll answer that in the last minute. But before that, there is more. So there is a row 2, and this is the Lagrangian for row 2. There is an invariant theta. Here we have two formal variables, t1 and t2, and t3 is just the product of the two, and we have to integrate over 6 variables for each edge. So p1i, p2i, p3i, x1i, x2i, and x3i. And the Lagrangian is a horrible mess. Again, I have nothing good to say about it except that it works. Here is the verification of Reidemeister 3. And again, the answer is that it works. You can compute it for the trefoil. And this is the invariant theta that I mentioned before. And I want to say a few more words about it. Okay? So you see the main point of theta So it's a two-variable polynomial, Laurent polynomial. And then there is you know what, I'll skip the faster program. I'll just tell you that there is a nice way of visualizing two-variable polynomials. So basically, okay, let's start with a one-variable polynomial. If you have a one-variable polynomial, it's a list of coefficients. And the list of coefficients, you can turn it into a list of colors. Make the positive coefficients red and the negative coefficients blue, and you get a sequence of reds and blues, and let's call it the barcode. Okay? So, in fact, here is the barcode for the trefoil knot, or the Alexander polynomial of the trefoil knot. It's red, blue, red, because the coefficients are positive, negative, positive. Okay? But if you have a two-variable polynomial, so if you have a two-variable polynomial, then you get a two-dimensional array of coefficients. And each one can be red or blue. So you get a two-dimensional array of colors, of pixels, and that's a QR code instead of a barcode. Except it's kind of better to take the coordinates to be not quite perpendicular. So rather than using a perpendicular coordinate system for the two powers of the two variables, you use one is in the direction of positive x-axis, the other one is in the direction of the cubic root of 1, a non-trivial cubic root of 1. So, so instead of kind of a standard QR code, you get a hexagonal QR code. And here is the hexagonal QR code of the trefoil knot. So here is the coefficient of minus t. So this would be the coefficient of 1, and it's 0. The coefficient of t1 is also 0. The coefficient of t1 squared is negative, so this is blue. This is t1 squared times t2, so I went in the direction of the cubic root of 1, and that one is positive, so it's red. So this is the trefoil knot. Just for fun, I also computed the Conway knot and the Kinoshita-Tarasaka knots, mutant pairs, and their Alexander polynomials are both 1, so these are not very interesting barcodes, but their QR codes are completely different, and theta indeed sees mutation. Here are a few further examples. So these are the barcodes and the QR codes for various torus knots. This is the barcode and the QR codes for the torus knot 22/7, approximately t sub pi. This is the barcode and QR codes of 300 crossing knots. So let me emphasize, for most other knot invariants, just saying 300 crossings is science fiction. Computing invariants of a 300 crossing knot is science fiction. This isn't science fiction. Here is the results. Here is the result. The result seems to have some patterns in it. I have no clue where they're coming from. Okay? An unproven fact, so experimentally, but also for various theoretical reasons, we know that the degree with respect to T1 of theta is less than twice the genus of the knot. Strictly speaking, it's unproven, but there is no doubt that it's true. The evidence is just overwhelming. And here is an example. So this is the 48 crossing Gomb-Sharman-Thompson knot, which might be a counterexample to the slice ribbon conjecture. And here is the invariant of the barcode and the QR code of that knot. It was computed, by the way, in 17 seconds. And if I compute the exponent of t in the Alexander polynomial, it's 8. if I compute the exponent, the power of t, the degree in t2 of the theta part of the invariant and divide by 2, the value is 10. And so theta knows things about this knot that the Alexander polynomial doesn't. It gives you a better bound. Okay? And here is only the QR codes of the knots in the Wolfson table. Again, just for fun, there are patterns in it. I have no idea what they mean. And now it's time to say where it came from. Yeah, I went way too fast. I wasn't supposed to have time to say where it came from. Everything okay so far? It probably isn't because I went way too fast. Anyway, I can tell you where it came from. I can also tell you that I don't really know, and where it came from is completely irrelevant. It came from some roundabout thinking which went very, very complicated in crazy ways, and that's not really where it is. The result is more, these things are more fundamental than where they came from, and so the answer to where it came from is, it's up to you to figure out. Or maybe up to us, we're working on it. And I think the answer has to do with the dream that I stated in the beginning. So it has to do with some, or one answer, one possible answer, probably there isn't just one, but one possible answer has to do with Lagrangian defined by low-order finite type invariants of homology classes on a ciphered surface for the knot. I think that's the correct kind of future rewrite of where is it coming from. But the historical way in which it came from, by which it came from, is completely different. So really it came from silly things in quantum algebra, and let me tell you in very few words what these silly things are. So in quantum algebra you end up looking at universal quantized universal enveloping algebra. So basically universal enveloping algebra with an additional parameter. Universal enveloping algebras are isomorphic by the PDW theorem as vector spaces to polynomial rings. So basically you have polynomial rings with funny multiplications on them, right? Because the universal enveloping algebras are all isomorphic to polynomial rings, but with the wrong multiplication. So if you can import the multiplication from the universal enveloping algebra to the polynomial ring, and then you get a funny multiplication on the polynomial ring. Likewise, the co-multiplication will be some funny co-multiplication on a polynomial ring. So you need to learn how to write functions between polynomial rings or tensor powers of polynomial rings, which are again just polynomial rings with more variables. For example, the multiplication is the multiplication of a quantum universal enveloping algebra is some map from the polynomial ring tensor squared to the polynomial ring. So it's just some funny map from a polynomial ring to a polynomial ring. And then the trick is that there is an isomorphism. So if you want a homomorphism from one polynomial ring to another polynomial ring, and these are linear homomorphisms, not multiplicative, right? The whole point is that the multiplication gets changed. So if you have a linear homomorphism between one polynomial ring to another, you can write it as a generating function. This is isomorphic to power series in variables dual to the variables here with coefficients, polynomials in the variables that appear here. And I think of this as a generating function. It's a function of two variables, or two sets of variables, that encodes a homomorphism between two polynomial rings. Now, you need to know how to compose. Basically, you need to know how to compose maps between polynomial rings. Because, like if multiplication is a map between two polynomial rings, if you want to check associativity, or if you want to do iterated multiplication, you need to know how to compose multiplications. So you need to know how to compose the generating functions corresponding to homomorphisms. And then comes a funny thing. You can write a formal formula, which is kind of true up to the laws of formal Gaussian integration, that the composition, the generating function of a composition is equal to, you multiply the two functions and you integrate it against a quadratic, the exponential of a quadratic form. Then the last thing is that you need to be careful which quantized universal enveloping algebras to work with. And oh my God, by now I'm over time. But there is a little bit of a story that tells you that like the UQ of G can be not quite deformed, but degenerated, to be shown to be a degeneration of a family UQ of G epsilon. So, and then when epsilon is equal to 0, everything turns out to be easy, so you write things as powers of epsilon. You expand everything in powers of epsilon, and then it turns out that all the structure homomorphisms, which mean all the structure generating functions, are Gaussian. The integration, the composition is, again, the integration of Gaussian things, so that's exactly the techniques that I've introduced before, and it boils down to the formulas that I wrote about. This is wrong. This is absolutely wrong. This will not stay the right way to see these things, but it is at the moment the correct history of how we got to these things. Thank you for bearing with me.